So I'm Rob Berger, Chief Architect at Informed, and I've been around the computing and software, cloud, everything kind of DevOps from probably before the beginning. Sometimes I feel like the Forrest Gump of computing, seeing so many different things. Kind of been the whole real full stack, all the way from hardware through up to the front ends. And my head's been in the clouds, primarily at AWS since 2008. And I've had roles as founder, CTO, VP of engineering, and chief architect. But I'm still hacking after all these years. So warning, there will be no generative AI in this talk, except a few gratuitous DALL-E images and the following. So I gave ChatGPT the prompt, you're Werner Vogel's CTO of AWS, but you're moonlighting as a stand-up comic. So tell me a joke about managing complexity of a large serverless SaaS. So ChatGPT replied as the cybernetic Werner Vogel's, why do I love serverless architectures for managing complexity? It's because it's like hiring a team of ninjas for your IT department. You don't see them, you don't know where they are, but somehow the job gets done. But then you get the bill, and it's like, so they were here all the time. So clearly comedians don't have anything to worry about, but Berger should watch his back when Q is about. So I work at Informed, and Informed is a company that does income verification, fraud detection for the auto loan industry. And we do that kind of through document intelligence, applying ML models and heuristics. So we basically get as inputs. Everyone here has probably done a car loan, and they have to fill in those giant applications and supply all these documents. We get all that as inputs from our lenders, and we do these various stages of classification, extraction. We pull out all the information and then verify the stipulations that the lenders have, and we give back to them, a kind of a grade and what all the application data meets. And by doing this with ML and things, we're able to increase the accuracy, and what normally they had like rooms of people doing and taking days, we can give a response in minutes. And our customers are some of the top lenders and banks. We've done over $110 billion of loans, which is about 8% of the US car loans. And with banks being our customers, that kind of creates interesting constraints for us, because they all have like tons of regulations and compliance. And the most scary thing for me is we have just infinite PII. So that really puts some interesting constraints on what we can do. So what I really want to talk about is the evolution of Informed's technology stack, which I joined about almost 3 years ago. When I joined, it was kind of like the typical startup that's been around for several years. As a startup, when you start up, you actually don't really know what your business is. And it takes, a few years wandering in the desert, trying different things. And your infrastructure and software tends to reflect that. So when I joined, they had accumulated quite a bit of tech debt. And you don't really have to care about the details, but this is what the environment was when I joined. It kind of had a big Rails app kind of at the center that kind of morphed into craziness, talking to about every AWS service in existence, primarily through Elastic Beanstalk. And it was all, like every one of those blocks talked to a single Postgres database. They used the database as kind of the messaging bus almost. So when I joined, I was tasked to, how are we going to move this to a point where, as part of having such a kind of big monolith, development kind of froze. It was really hard to add a new feature. So we really wanted to come up with something that would both make it easier to do development and lower costs and improve performance. So, and at the same time, surprisingly, they made the decision to actually do a clean break from the old system to the new system, which is generally pretty scary. So I think there was a lot of bravery to do that. At the same time, we changed the API from XML to JSON. So it was a really big change. And I wanted to move to a completely serverless environment because we didn't really have a big ops team. The company's got probably about 50 developers total. So we really wanted to move to something kind of a event-driven modular microservice architecture. But wanted to do it in a way that didn't incur the full risk of a complete break. So we kind of applied the strangler pattern where we actually took big chunks of the old code and first ran it as that, but we kind of unwired it so that we could actually use EventBridge and webhooks to turn it into kind of the modular pattern we want, but still with kind of that monolith at the core. And then all the new services became serverless Lambdas communicating to that through the EventBridge model that we wanted. So that allowed us to kind of quickly get something going and actually have customers testing it in 6 months and production in 9 months. And then from there, we really started evolving into the true microservice architecture. And I kind of describe it as a fractal architecture pattern where you kind of have a top-level thing that manages the whole app. When I say application, that's the loan application, kind of is the element of a pipeline stream. And then it kind of recurses down these steps of subsystems. Each one has an orchestrator. And today, those orchestrators are step functions. And that will then kind of delegate the sub-steps to another subsystem. So it's kind of a fractal architecture. And today we have about 107, we call them topologies. Each one is a step function, and about almost 340 lambdas. And it's a mix of Python, Ruby, and Node. So that's kind of the journey we took from an architectural point. The focus of this talk is really about the tools and techniques that we developed to kind of manage this level of complexity. And complexity really is the main issue. Once you get past, tens of lambdas and stuff, once you start getting to the hundreds, it's managing that complexity becomes the main focus. So, we're told that serverless is supposed to make things simpler. It's in the name, it's less servers. But complexity, again, is the management. And as well as being able to deliver a developer experience that can support fast iterations and distributed developer work as well. And then release management is also something that you have to really deal with. And so we found that the existing tools just didn't match that complexity of the dev workflow that we wanted. So, this is sort of a little bit strange to say at an AWS thing, but we hate CloudFormation. And it really doesn't match kind of Lambda or serverless type activity. Mainly it takes a long time to run. You get kind of weird circular dependencies and failures. And our platform team basically didn't want to touch it. So we looked at other tools, and so a bunch of them, at the root, are all still CloudFormation, which is unfortunate, because some of these tools are pretty nice, though we found that most of them still don't help you with the level of complexity that we have. Most of these, other than like CDK, are focused towards kind of front-end oriented development or very small systems. So we really kind of rejected those. In Terraform, it sucks less than CloudFormation, in our opinion. And the team was pretty familiar with it. But it really still doesn't have the right impedance match to the kind of distributed system that we wanted to build. It's still very low level. So we still use it kind of to build the bones of our system. And as we'll go in, we develop tooling ourselves to do the bulk of it. So we use this to build like the VPCs and the IAM roles and things like that. So kind of what we really were looking for is a way to abstract the system in a kind of the way that you do in software. And kind of the concept we were looking at is that the cloud is the computer. We wanted to have a way that we can represent and deploy the entire system or any subtree of the system. As I showed in the beginning, you can kind of see we have a hierarchical structure of our system. And we wanted the tooling to be able to deal with it in that kind of a form. We also wanted to have tooling so that the developers were able to do fast development cycles of these subsystems. So again, the idea is that the cloud is the computer, and we wanted to be able to map the entities of the system, like events, mutations from like AppSync, routes from API gateways, Lambdas, and step functions into higher order functions. And we call those cloud functors. So we're kind of applying functional programming techniques to cloud infrastructure was the goal. Could you hand me the water there? No, thanks. So what we wanted to be able to do is kind of compose and represent and deploy the entire system or any of these kind of subtrees of the system, and have a kind of a simple YAML or JSON declarative description of the system or of the components and thus the system. And another key goal was to be able to decouple the system description, make that kind of abstract, and then be able to independently render it to the cloud in specific environments or sandboxes. So the topology.yaml is kind of the concept of description that describes what we call the functor. And that would describe an abstract service of states, like in step functions, routes, events, queues, et cetera. And then this becomes the primary level of encapsulation. And the other part of the idea is that the layout of the file system should also represent the hierarchy of the system. So we have a monorepo, and we have kind of the top level of the services or the core services, and then within them are all those subsystems that are described. And you can work at it at any of those levels. So that's kind of the goal. That was the dream. Then we had to really figure out how to create some tooling, because the tooling to do that, we couldn't find that anywhere. So we developed a tool that we call TC, which is a graph-based contextual stateless deployer and workflow tool. So this is the mechanism that will take those kind of descriptions and the file system hierarchy and create a software representation of that then could be processed by other parts of the tooling. And then the goal is, again, to empower the developers to focus on the development of the application and not worry too much about the infrastructure. And another key goal is composability. That you can take those components and either reuse them or structure them how they interact with each other very easily. And the tool itself is actually written in Rust. I'll just touch on that later. So the services, the AWS services managed by the tool, are here primarily step functions, which we use for flow control and orchestration, the Lambdas for compute, et cetera. So these are kind of the core components that is managed by the tool, which for us is really the main things that are different and change rapidly in the system. And so the pattern is that the functor is what we call this boundary of encapsulation is defined with that topology.yaml file. And it's made up of several things. The first being orchestration, which is the step function. And the step function then controls and drives all the Lambdas. And the step function, the functors talk to each other primarily through EventBridge, but then the state machine drives the Lambdas primarily through direct invokes. And then the Lambdas kind of are what we use to implement the business logic. And the goals there is to really have the Lambdas as pure functions. So Lambdas as Lambdas. There's nothing that enforces that, but that's sort of a design goal. And then the subdirectories within the functor contain the Lambda code. And that's also the convention, that if you don't specify anything, when the tool walks down the tree hierarchy, it looks for Lambdas within those subdirectories. And the step function handles all the error handling and recovery. And that turns out to be a really nice pattern. So the Lambdas, again, are as side effect free as possible. And the state machines kind of can pull all the errors and have them handled in a very uniform way. That also really helps in observability as well. And there's very little I/O in the Lambdas themselves. We do use S3 as a way to pass data between Lambdas. So the messages or the invokes would have pointers to S3 objects. That's mainly because we're dealing with pretty large chunks of data as inputs, mainly image data and large documents. The tool itself is written in Rust, and a few reasons. One of the primary ones is the rich data structures that's available in Rust really helped in terms of, we create this data structure that represents this tree of services. So having a rich set of data structures helps with that. It's also easily distributable as a binary. And we were able to add a kind of a plug-in mechanism to make it extensible. And that plug-in mechanism can support other languages as well. So the tool is made up of several modules. And they can be kind of split up in two. The first being the kind of the modules that support that build and deploy cycle. And then the second set is the tools that help the developer do their daily work. I'll kind of go into detail for each of those. So at the core is the compiler. This is what maps that abstract templated system definition that's in the topology and in the subdirectories. And the compiler itself is totally abstract. It doesn't take into account anything that's like account or environment or the deployment target. And as we mentioned, the key abstractions are these here, the things that drive those things, the AWS services like step functions, AppSync, Lambdas, API gateway, et cetera. So then the next part is, when you're building Lambdas, you have the Lambdas themselves, and then you have all the kind of assets to support that. For us, that's primarily Lambda layers, and many of our Lambdas are actually ML models. So we have a bunch of very specific ML models that do like extracting certain fields and classifying different documents. So we have like, a few hundred ML models, and they tend to be pretty big. So both the models, but actually it turns out the dependencies are what's really crazy big. Oh, the PyTorch and Tensor and all that stuff. So we ended up putting those into EFS. But you need to be able to manage that. You want those to be versioned and a deploy cycle. So this handles both the pushing those up into whatever either S3 buckets or Lambda layers or EFS, and keeping track of their versions. And this allows us to manage it both in the development and the deployment or production cycles. Then the builder is the part that actually builds the Lambdas. And we have the issue that people are using laptops, it might be a Mac or something like that. So the builder handles, first of all, managing the dependencies, knowing what's in these deployed assets, as well as local dependencies, and it builds it in Docker containers so that it can target different AWS runtimes. And we can support various different languages here. So there's nothing really tied to specific languages. The resolver is what takes the compiler output, which is that abstract representation of the system, and turns it into a concrete plan, effectively, just like Terraform kind of creates a plan. This tool is what takes that abstraction and turns it into a plan to deploy. And we use the AWS SDK to do the updates. But that'll be the next step, actually. So what this does is it takes various inputs that you give it when you call it to resolve, that then specifies things like the namespace, sandbox, environment, et cetera. And it also can talk to the AWS environment to get the current state of the target. So as opposed to Terraform, which literally manages its own state representation, we consider the deployed environment the state. So it's like, the only real definition of the universe is the universe. Similarly, in a system, the only real definition is the system itself. And then this generates the concrete plan, which the next step, the deployer can take, and this acts kind of like the equivalent of a Terraform apply, but it uses the AWS SDK to actually do the updates. And it has a kind of a concept of a CRUD interface to do that. So the deployer can do both creation, updates, and deletes. And then the releaser is more about kind of managing the the Git tag and the release cycles of the software. We use the Git tags as the way to kind of be able to record what's deployed at any environment, and we can use that to recreate an environment or to roll back as well. And this also can do stuff where, we talked about the fact that we can support sandboxing. The sandboxing can happen in any environment, and not only can we sandbox like the Lambdas and the state functions, but also the routes and AppSync and EventBridge stuff. So this would actually be able to hook that up so you could do things like blue-green deployments or multiple environments or multiple sandboxes in the same environment. And then the tooling for the developers contains some things like the invoker, which the developer can use on their laptop to invoke either individual lambdas, functors, or a tree of functors in the cloud. So this allows them to supply a payload and trigger something in the cloud, but it also has a REPL so that it's kind of hooked in, and you can kind of interact with it directly while you have it invoked. So we found the developers have found this to be really helpful. And then today we can run Lambdas locally through a Docker container, but the emulator knows about the layers and the other assets, so it can hook them up properly locally as well. And we're working on things so that we could do a full functor run locally, including the step functions and AppSync and stuff like that. So that's going to be kind of like similar to Amplify Mock. And then we have a mechanism we call Bootstrap. We're not really using this internally that much, but this would be the way, as we open source this, people can use this to extend this to work with other target environments. It would mainly be for extending the deployer. So that kind of explains the concepts of the tool. The way it's used is, I just want to walk through kind of a development cycle that a developer would go through using the tool. So let's say you're going to create a new functor, a new subsystem. You create a directory with the same name as the functor, because we use the naming of the files and the file directories as conventions. And then you can use the scaffolding command to create kind of the stubs and everything, which at that point you would then start writing your code. You would fill out the topology.yaml with any kind of events and API gateway routes. So the tool doesn't actually deploy the API gateway. That's one of the things that Terraform still does. But it will update the routes and things like that, because the routes are really specific to the functors. Similar to, same thing with kind of EventBridge. The EventBridge bus has been created by Terraform, but then you get to specify the rules that are specific to each functor. And then the big work is usually writing the code for the Lambdas. So, and you can do that just using conventional, whatever your tooling is. We tend to use Poetry for Python and Bundler for Ruby, stuff like that. At that point, you can use the tc build command, and it would actually build everything that needs building, primarily the Lambdas, and then publish would push the assets, like the layers, up to the cloud. But you need a separate function that will actually do push the Lambdas themselves and the step functions and things like that. And that's the tc create. And this is where you now specify the targeted environment and sandbox name. So this is where it'll actually, in the dev cycle, you're going to push this probably to a dev environment. And we allow our developers to do this directly. And they can then use invoke to test it out and stuff like that. They can invoke either the individual Lambdas or the functor, the step function as a whole. So let's say they've done some testing, they realize they need to update it, they change their code, or they change any of the configurations. They can then just run the tc update with the same kind of parameters, and that would push their changes up to the cloud. And this is a very fast cycle, so there's really no waiting. It just pretty much instantly updates them. And you can use this to also update any of the other mechanisms, like the API gateway routes or EventBridge configs and stuff. So then, let's say at that point you've kind of finished, you've got the things working. If this is the first time you created this functor, you just need to create a configuration for the CI/CD to deploy it to further stages. And we use CircleCI, but there's really nothing that's specific to CircleCI. Because what happens, we use the CI to actually call the same, to call the TC commands themselves. So just as the developer was calling the commands on the command line, the CI can also call commands, but the CI has its own permissions, so it can do it to upper environments that the developers can't do. So the way we work is the developer can effectively release it to QA, and then at that point, after QA has approved it, the CI can then push it to the upper environments. And it's mainly doing the tagging and the actual deployments. So once QA has approved it, they can then do promotions either of the entire stack or individual subsystems, by just saying sync, let's say, staging to QA, and then once they approve it in staging, staging to prod. So it's a pretty easy process for them, and the developer can tear down their environments with the delete, and it's easy to see what's kind of in there with the list. So this is a tool that we've developed in-house. Giving this presentation kind of gave us the urgency to release it as open source. So we're just doing that today. Actually, it probably won't be out till next week, but the site is there. But I have to say that this is a tool that we've used in-house, and we don't really know what it's going to be like for other people to use it. So if you're into experimenting, we would really appreciate you giving it a try and giving us feedback. We think that this is something that would be useful to other people. But we welcome feedback and contributions. So I think with that, ready for questions?
Local testing, local development, local stack.
What is it called? I didn't hear the name.
Okay, I will repeat one more time. Anyway, it was a really good presentation. So my question is, have you considered using local stack?
Local stack.
Local development, because it feels like you are repeating what these guys are doing already.
Well, I mean, I don't know if local stack would do what we want. I think it would be interesting to use local stack with this tool. You know, have local stack as a target. At least from what I understand, what local stack is. We looked at it a while back and haven't really looked at it for a while. But I think that it could be interesting to use it together.
Any other questions? All right.
Has to be some questions.
All right.
Can you please go back to the fractal architecture patterns? Yeah, perhaps can you explain it, because I missed it.
So the idea with the fractal patterns is we don't really show what's happening in the application orchestrator, but it's a very similar pattern as this, where you can think of that as the first stage of the system that's pulling in the data and kind of orchestrating the entire flow of an application. The application, again, being a lone application, which is kind of the wrapper of a process. And then the documents are effectively fed down to the document orchestrator, which then orchestrates these other stages, as I showed before, which is like classification. And then within classification, there's kind of recursion into multiple functors, each one with their own orchestrator, doing very specific things, like there's steps for just identifying bank statements or something like that. Similarly with extraction, the extraction tree is very deep because we actually get down to like social security number identification, address identification. Each one of those is a kind of a separate step or a series of steps. So that's what I mean by a kind of a recursive fractal pattern. It's the same pattern of orchestrator processing and then a recursion down to additional orchestration and processing.
Do you guys do any with TC commands, anything that's like contextually aware in your monorepo? So instead of dealing with like YAML defs at the top level, you can just be in like some subfolder and run commands in it.
So that's a key point, is the idea is that so you can think of this as a tree of these recursive or fractal patterns. And you can go anywhere in that tree and say, build or deploy, anything at any point, all the way from the top to any individual or any subtree. So that's definitely one of the key features of the service. And there's not a topology.yaml that describes the whole system. The compiler pulls that together and creates effectively an AST of whatever point you're descending into that tree.
Time for one last question, if anyone has any questions.
All right, well, I have one then, if no one else does. Do you have any data around the efficiency gains that you got by implementing TC?
Well, so before, I don't have like exact numbers, but before, there became a point where people were kind of drowning in the complexity. There's a whole cultural aspect to this as well. When they first did the first kind of resolution, we had this pattern, but we were using Lambdas as the orchestrators. Just the concept of switching to step functions was a big cultural change. And there was resistance, but then once they started using it, it was like an oh my God moment for a lot of the team. And they've really embraced it. And the speed of being able to implement new features has just zoomed. I mean, it's dramatic. And including what was interesting, I said I wouldn't talk about generative AI, but we did get this mandate to employ LLMs as part of the processing. And we were able to just drop it right in. It just became another processing element in this hierarchy. It works actually pretty well. Yeah, it's been a dramatic improvement of the developer productivity.
Great, thank you.
Well, thank you very much.